we will begin. So first, welcome and thank you all for joining us today. It's my pleasure to introduce our speaker, Dr. Giorgia Di Capua. Dr. Di Capua is a postdoc at the Potsdam Institute for Climate Impact Research, and she is also a PI leading a Horizon Europe project, which explores predictability of extreme weather. Dr. Di Capua completed her PhD at University Amsterdam with a focus on the Indian monsoon and its interaction with mid-latitude circulations. Her research emphasized causal analysis in climate science, especially in interconnection between tropical and extratropical regions. Giorgia's talk today will focus on the application of causal inference to investigate how local and remote interconnection influence summer circulation patterns and heat wave probability. Please join me in welcoming Dr. Di Capua. The stage is all yours, Giorgia.
Thank you so much, first of all, for the invitation and for the really nice introduction. And okay, so I will start with my presentation now, which, as you said, is about like applying causal discovery to studying teleconnections, atmospheric teleconnections, and specifically teleconnections that lead to changes in summer circulation in the Mediterranean. And I will, let's just see that. Okay, works. So I will start by giving you like a general introduction on causal discovery and specifically the algorithm that I'm using, which is the PCMCI algorithm. And then we will have a look at how this PCMCI algorithm has been applied in climate sciences. And then the, let's say, bigger part of the presentation is about the Indian monsoon, Indian summer monsoon, as a driver of heat waves in this Mediterranean. So just starting with the introduction on causality, the main idea of causal discovery is to identify causal links among or like in a set of one-dimensional time series. And of course, you will know that correlation does not imply causations. For example, the number of sunburns and the number of ice cream that have been eaten may correlate, but of course, there's no causal link between them. The common cause is the hot summer weather. So correlation is, however, correlation and cross-correlation is, however, a nice way to have a first idea on whether time series share some behavior. However, there are like drawbacks or like phenomena that can inflate correlation or cross-correlation. So for example, correlation values can be inflated when we have autocorrelation in one or both time series, or when we have, for example, a common driver, like in the example above, or when we have indirect links. And so the main idea of these, or any causal discovery algorithm is to try to identify or eliminate the spurious links and identify the true causal links. And of course, the word causal always stands on a set of assumptions which need to be respected. And so in this specific talk, we will focus on one of these causal discovery methods, which is the Peter and Clark momentary conditionally independence PCMCI algorithm. So just to give you an idea of why we want to do this, this is actually the beginning of my PhD work. And for my PhD, I was looking at the interactions between the Indian summer monsoon and the mid-latitude circulation. And we started from a paper by Ding and Wang, which shows that the circumglobal teleconnection, so this wave pattern in the mid-latitudes, is correlated with the monsoon trough rainfall. However, of course, this analysis was based on observation and on correlation values, and the idea that we wanted to pursue, or like our research question, was to assess whether this link was causal. And of course, there can be other drivers involved when we want to look at what drives the variability of the Indian summer monsoon. Just to give you an example, the Magellan-Julian oscillation. And what we did was basically apply this method to obtain causal effect networks, where we can actually see the direction of the causal links, and also other like application of PCMCI, like for example, the RGCPD algorithm, which allows to identify spatial patterns that affect certain variables. And the main result here was that we actually find this network that summarizes the results, where we see that the Indian summer monsoon system is connected with a two-way causal interaction with the mid-latitude circulation. But how do we go from one-dimensional time series to a causal effect network? The idea is to use PCMCI, and the good news is that this is actually not a black box, so you can actually check each step that the algorithm does. And I'm not going to go in too many details on how the algorithm works. If you're interested and there's time for it, I can say more at the end. But just to give you an idea of how this works, PCMCI, so the main goal is to distinguish between spurious and causal links. And to do so in the linear framework, it uses partial correlations. And basically, it's like iteratively checking whether pairs of variables or like the correlation between pairs of variables can be explained by a set of one or more third variables, which are called actors. And okay, so at the end of the algorithm, it gives a set of causal patterns, which can be represented in what we call a causal effect network. And here I'm gonna just tell you how to interpret this plot. So in this case, we have 3 time series, and you can see different errors that show the direction of causality, and then they show the strength of the link, and I will tell you in a minute what this beta coefficient means. So the link can be positive or negative, and if it's positive, it means that when actor 2, for example, increases its value at a certain leg, then at leg 0, actor 3 will also increase, and if it's negative, it means that, for example, actor 1 is increasing and in a certain time steps, and actor 3 is decreasing, or vice versa. And the number represents the leg. It could be hours, like it could be years or months. The important thing is that all the time series have the same time resolution. And as I said, just a few words on what this like beta coefficient is. And so if you imagine that we have identified the set of parents for A. For example, A depends on itself at leg -1, which is shown by the color of the circle, B at leg -2, and C at leg -1. So the beta coefficient, which gives you the color of the arrow, is the coefficient that you get from calculating the multilinear regression of A at T0 on its parents. So for example, the influence of A on itself gives you the self-causal effect, which is this circle here, and the other 2 beta coefficients give the causal effect of the other 2 variables. And so I will first give you an idea of some applications of this algorithm that well, I chose some of my work or work that I've been directly participating on, just because I'm more familiar with it. But actually, this tool is, let's say, available since about 10 years now. And I must say, when I go to EGU or AGU, I start seeing many applications, also by people that I don't know. And at the beginning, it was, of course, a very small group that was applying this method. So to give you some examples, the first example is what we have seen before. So here we look at tropical, extratropical causal pathways, and we use PCMCI to kind of testing these hypotheses or a certain hypothesis, and this can be done in observations, and of course has some advantages if compared to using model simulation and so on. Another application is using the causal precursors that are identified to provide long-range statistical forecasts, in this case for precipitation, but it's been used also for hurricanes, variability, and crop yields in North Africa. And another way, or like slightly different application, is to kind of go from the one-dimensional network to a 2D field, like in this case here. This is really just a follow-up work from this first paper, and here we look at the influence of the South Asian monsoon on the northern hemisphere. And here basically you can imagine that there's like a fixed network that in this case has 3 elements, and one of the 3, it's not a one-dimensional time series, but it's a field, and the network is calculated for each grid point. So like 2 actors are kept the same, and the third one changes for each grid point. And this is basically telling you where you see a causal influence by a certain pattern. And it's useful because, of course, in this specific example, the South Asian monsoon was like, by definition, strongly or highly correlated with the circumglobal teleconnection. And the idea was to check on a 2D scale where the influence, where we could see a causal influence from the South Asian monsoon and disentangle it with from that of the circumglobal teleconnection. And another example of application is actually to use this method to validate forecasts or climate models. Specifically, in this case, this also like a follow-up of this paper where we basically check how these tropical, extratropical teleconnections on a 2D scale are reproduced in seasonal forecasts from the ECMWF. And here, for example, we check the values of like the relationship between the Indian monsoon and North Africa, which is also called a monsoon desert mechanism. And you see that the distribution of the model is, let's say, shifted towards lower values, and the observed value from era 5 is actually completely outside the distribution. So actually, shows here like the most extreme case. In the rest of the field is not so extreme, but this is really just the best, or like the case where the underestimation is the most extreme. And of course, there are other ways to provide a causal analysis. I'm always focused on PCMCI, but for example, with some colleagues, earlier this year, we have published a paper that compares the Liang-Kliman information flow, which is another way to assess causality, which is quite different, and PCMCI. And actually, in general, we find quite consistent results. Each of the 2 methods has some strengths in certain specific cases, but they first both show much better ability of like detecting causal links than correlation. This is a little bit obvious, but it's also nice to kind of have a case study with some theoretical models where we actually can control or like know a priori which are the real causal links. And so they both do a good job, but with some differences. And another application, and this is actually work that is in review, and it's very close to be accepted, It's on improving the forecasting skill of global climate models, and in this case, we use the MPI large ensemble model to basically study the connection between summer East Atlantic variability and temperature over Central Europe. And another work in review by another colleague here at PIC is analyzing the atmospheric patterns that lead to both single and compounded streams, and we kind of show how to apply this method to, let's say, not a case study, but to kind of extreme values, because by construction, this method is actually better to look at the climatological mechanisms or like causal links, but there are also ways to kind of use it to study more like extreme or like drivers of extreme events. And well, this is really work in progress. We are also, we want to apply causal discovery also to study impacts of extremes, and we have a work in progress on causal drivers of fire weather in the Mediterranean area. And okay, so I'm gonna go on to the let's say third part and longer part of this presentation. So this is work in progress, which I should present at AGU. Unfortunately, I cannot travel, so a co-author will present it for me. But so this is work that is done in the context of the PREVENT project, which is this Horizon project that Shan was describing before. And the idea is to look at the influence of the Indian summer monsoon on the Mediterranean circulation and therefore on heat waves in the region. And yes, so as I said, this work is in preparation, and hopefully I will be able to submit soon. Okay, so I first need to give you a little bit of an introduction on the region that we are analyzing and some climatological characteristics. So we are looking at summer, and we are looking at winds that are called Etesians. And so these winds are northerly winds that characterize the background flow in the Eastern Mediterranean region, so like this region here. And here you can see the climatology of meridional wind at 850 hectopascal, so more or less 1.5 kilometers up in the troposphere, and for June, July, August, and September for RFI. And you also see the region where these winds are identified. So this, so the Etesian index is defined as the spatial average of the meridional wind over this area. So when we have strong, this is the climatology. So you can see that climatologically we have like northerlies over this area, and these winds are actually also important for the monsoon activity in the Sahel region. And so they show a peak in, so the activity of the Etesians is strongest in July and August, which coincides also with the strongest activity of the Indian summer monsoon. And if we look at the mean sea level pressure climatology, you see that we have a climatological low pressure sitting, of course, over India, and this is related to the Indian summer monsoon system. And this low pressure extends to the Arabian Peninsula, and here we have the Persian low. And so basically, the Etesians, or like this climatological feature, arises because of like this east-west gradient. You see like high pressure anomalies over the Western Mediterranean and low pressure towards the east. So that's why we have these winds here. So it kind of makes sense to think that the activity of the Indian summer monsoon may influence this region. And this is also something that we know is happening in general. So I was briefly mentioning the monsoon desert mechanism that basically tells us that strong convective activity in this area is warming up the troposphere, and it's acting as a source of Rossby waves activity, which basically increases the subsidence over Northern Africa. And this is related to these winds as well. And of course, these winds are quite an important feature in the area. They can mitigate heat waves because actually they bring, they are back cooler air from Eurasia towards the south, but they are also important for tourism, navigation, air quality in big cities, and they are also potentially like inducing or like helping wildfires to develop. And so the idea of this work is to actually check whether the Indian summer monsoon has an effect, or what is the effect, or like quantifying the effect of the Indian summer monsoon on Etesian outbreaks, which are periods of enhanced Etesian activity, and how this can enhance or mitigate heat waves depending on the phase. Okay, so to do this work, I have been using both reanalysis data, again, from the ERA5 dataset. I'm using 3-day time steps or monthly, and I'm using meridional wind velocity, geopotential height at 200 hectopascal, temperature at 2 meters, sea surface temperatures, and outgoing long radiation. So this last variable is actually quite useful to assess convective activity, especially in the tropics and summer. So the concept is that strong convective activity leads to like convective clouds, which are cold at the top, and therefore we can kind of distinguish when we see like lower OLR anomalies, we know that there's convective activity in the area, and when we see higher OLR anomalies, we know that we have clear sky conditions. And the other dataset that I'm using is the System 5 seasonal forecast dataset from the ECMWF. And so in this case, it's fully a model, and it's also good to use ERA5 and SIS5 together because the core models, so the atmospheric model is IFS, so it's like the same core model, but of course this is not used in the reanalysis sense, but it's used to provide forecasts which are initialized on the 1st of every month. And for now, I'm using seasonal SIS5 data initialized on the 1st of May. But I will also repeat the analysis for another initialization date because it's important to show that the results are consistent. And the main advantage is that we can have a full general circulation model that of course has all the physical mechanisms and way more data than observation because we have 25 ensemble members for each year. And the analyzed period is 1981 to 2023. And the, let's say, main advantage with compared to using maybe CMIP models is that in this case, it's initialized every year in right before our target season, which means that we have much closer agreement between the results of the model and the observation. Well, the historical runs of CMIP are initialized ones in the past, and so they can diverge much more with respect to the observations. And okay, so now I will give you an outline of the research. So we start just having a look at how the Etesians are reproduced in the model compared to the observation. And here we target July, August, and September, and this is all for almost all for 3-day data, and the Etesians are again identified over the same box. And so this is showing a composite of time steps with weak Etesians. So in this case, negative anomalies show weak Etesians, which actually corresponds to southerly winds or close to zero winds. And it's maybe not too clear, but the shading corresponds to ERA5 data. and the the solid and dashed line correspond to the ceasefire data. So you can actually see there's a very good agreement between the two, which is why I'm showing them in one figure. And you see the same here. We have the probability density function for the ERA 5 data in gray and for the ceasefire data in pink. And you also see that basically the two distributions are quite similar, and even like the 10th quantile, which is how we define weak Etesians, also are very close. And of course, these data are detrended anomalies, so they are centered around 0, and any long-term trend is removed, although to be honest, there's not much of it in this particular variable. And this is just showing the entire time series. And again, the pink is the distribution of the ceasefire. And in the last plot here, we have actually seasonal values and quantiles. And again, basically this shows like no trend, and there is a little bit of a bias in the total value of the two time series, but actually they are quite close, and the model is capable of reproducing the also like strongest weak quantiles. So it's like in general there's good agreement between ERA and ceasefire. So now we basically look at very similar plot, but this time we look at surface temperature. And as I was saying before, we want to see the effect on heat waves. And that's why we look at weak Etesians, because when the Etesians are strong, they attract cool air to the region. And when the Etesians are weak, this phenomenon is not happening. So that we can have a buildup of heat in this area, which is what is shown here. So this is the same plot. Again, composites of temperature for both ERA 5 and CIS5 for days, time steps, sorry, with weak Etesians. So you can see the anomalies go up to 2.5 degrees over Turkey, a little bit less over the other two regions. And we basically identify these three regions, so Egypt, Middle East, and Turkey. And over each of these three regions, we create a time series that represents the temperature. And then we want to see how the probability density function changes when we have weak Etesians. And to give you an example of what we want to do, here in this plot, which is for ERA 5 and for the temperature over Egypt, we see in like shaded color the climatological PDF, and then the solid line shows the PDF where we subsample for weak Etesians. And as you can see, the probability of exceeding the 95th and 99th quantile increases quite a lot. So this is also shown in these three plots here. It's basically the same concept. When the dot is not coinciding with the red line, it means, and it's like towards the right, it means that there is an increase in the probability of exceeding a certain quantile. And here we see an increase that goes from like 3 to 5 times more during weak Etesians. And the black dot here is ERA, and the purple dot is CIS5. And you can see that they agree with each other. And for the Middle East and Turkey, we see a similar behavior, although not as strong, with actually the model overestimating this mechanism, or like this effect for Turkey. So again, here there's quite a good agreement, and of course these regions show a trend, but again, for the causal analysis, the trend is removed, otherwise we cannot do that. So a few words on actually previous papers. So this work has been published earlier this year, and it goes really into the details of looking for mid-latitude and tropical drivers of the Etesians variability. Basically, to really just quickly summarize, we have two pathways. one from the mid-latitudes, where we have a Rossby wave that propagates from the North American sector towards and through the North Atlantic and then affects the Etesians. And then we have the Middle East ridge that acts as middleman between the Etesians and the Indian Sun monsoon outgoing over radiation activity. And here, just to specify, this link is negative because when we have strong convection, we have lower than usual outgoing over radiation, increased ridge over the Middle East, which leads to increased Etesians. And so the previous work that has just been published only looks at ERA 5. So now we want first to check how this mechanism is reproduced in CIS5 as well. And so we take very similar regions, we just adapt them a little bit because now we have only July, August, and September. And so these are like the three causal precursors of the Etesians. And we check how they look like in CIS5. And you see, I mean, there's qualitatively good agreement. Of course, there are some differences, but not strong enough to kind of force us to project these patterns in CIS5. So we keep what we find directly in CIS5, and then we produce this causal effect network. And here there are like three things to see. So first, the tropical pathway and the North Atlantic pathway show consistent result with the analysis that has already been published. And then we add the temperature over these three regions. And again, you see negative links here because this means that enhanced Middle East ridge or enhanced Etesians lead to lower temperature. And of course, vice versa, weak Etesians or like a weak Middle East ridge and therefore like a weak monsoon activity lead to increased temperature. And this is all assuming linearity. And of course, because in the model we have many ensemble members, it makes sense, and this always makes sense, to kind of check the variability of these links, so how stable they are, which is done in this panel here, where basically we produce 1,000 of these networks for CIS5, and then we see the distribution of the most important links, so like the link from the Indian Sun monsoon to the Middle East, from the Middle East to the Etesians, North Atlantic wave Etesians, and then the link with the strongest strength towards the three temperature regions. And what we see here is that in general, there is qualitatively good agreement because the sign of the link is always correct, with just a few exceptions in the tail of the distribution of CIS5. But it looks quite nice, although in general there's a little bit of an underestimation because the absolute value for ERA 5 is higher. And here we see an example where, for example, the effect of the Middle East ridge on the temperature over the Middle East is overestimated in the model, and for the Etesians effect on Turkey temperatures, it's actually really the case with the best agreement. So here we can be very satisfied in the sense that there's good agreement in the spatial, let's say, appearance of the precursors and also the causal links. And so the next step, we actually want to look at the influence of interannual variability of the monsoon on this type of links. And the reason for that is that so the Indian Sun monsoon has a strong intraseasonal variability, but it also has a strong interannual variability. And also because of heat's relevance for the Indian region, it's generally forecasted a few months in advance, both using dynamical models or statistical forecasts. And in this sense, if we can link the Indian Sun monsoon activity to increased or decreased probability of heat waves in the Eastern Mediterranean, we can basically have a little bit of an advantage, or like forecasting, some forecasting information to kind of characterize in advance how the season may look like. So in this case, we define the Indian summer monsoon as the convective activity over this entire box, and in ERA 5 and CIS5, and we are now looking at July, August, and September averages. So this is the entire season. We have therefore one field per year, and so in this case for ERA 5, we only have 43 years. So I plot the composite for the 40 years with the weakest Indian summer monsoon. And again, weaker Indian summer monsoon is represented by positive Euler anomalies. This is, you can think about it as like dry signal. And so the signal in CIS5, it looks quite similar. And just to remind you that, however, here, taking more or less the weakest 10% corresponds to more than 100 years. So of course, the sample is very different, the sample size is very different. And if we look at the effect or the composite for the geopotential height, we see negative anomalies over the Eastern Mediterranean and Central Asia, which makes sense if you think about the monsoon desert mechanism, which would tell us that stronger convective activity gives us like a stronger, like a higher anomaly over this region. And we also see negative values or anomalies for the meridional wind on the Eastern Mediterranean. And so if we then look at the activity or like the temperature changes in the Eastern Mediterranean, we see again for ERA 5 and CIS5, there's a tendency to have higher anomalies over Northeast Africa, a little bit, but not so much over the Middle East. Actually, we have a cooling signal over Turkey, and the biggest discrepancy between ERA and CIS5 is over the Balkans, because we have a warming signal over in ERA 5 and a cooling signal in CIS5. So this is now exactly the same type of plot as I showed you before. But in this case, instead of sampling the PDF based on time steps, like single time steps that show weak Etesians, we select the entire fourth season for ERA 5 that show a weak Indian summer monsoon. So for Egypt, you see that there is still an increase in the probability of having temperature above these like 3 quantiles, which is stronger in ERA, but is reproduced also in CIS5. And for the other 3 regions, actually for Turkey, there's not much of a change in the quantiles, in the higher quantiles. And for both the Middle East and Greece, there's a positive signal in ERA, but not, or even negative in CIS5. So here we start to see that there is some agreement, but there is also some disagreement depending on which region we are looking at. So the idea is to kind of understand why we have these differences. But before doing that, or like maybe one way of doing that is to check for changes in the network, or that are like historical changes, or changes that are due to maybe the presence of certain background circulation states. So for example, a strong Indian summer monsoon year may actually see changes in the network. This doesn't have to happen, and I check all these like links, and I only plot the few cases where there is a change. So for example, when it comes to historical trends, we only see an effect in ERA 5 or like a decreased effect of the North Atlantic wave on the Etesians on average. And when it comes to strong or weak Indian summer monsoon years, we basically see a stronger effect of the Middle East ridge on temperature over Egypt in absolute value during strong Indian summer monsoon. And also here you see that the effect of the North Atlantic wave is stronger during weak Etesians. And it kind of makes sense, weak Indian summer monsoon years, which makes sense. You can think about it like when Indian summer monsoon is stronger, the effect of the North Atlantic circulation is not as high. And we also check for El Niño and La Niña years, and we see that again during La Niña years that generally are linked to stronger inner monsoon. The effect of the inner monsoon on the Middle East region is higher. And we do the same type of analysis also for monthly data, because when we we see there's good agreement with 3 days, so like short time scales, but we see more disagreement when we go towards interannual variability. So we thought, okay, let's have a look at what happens with monthly data, and basically what we see here, and I'm gonna try to finish in the next couple of minutes, is that in general, some of these links are well reproduced, or they are in the variability of the model, but there are, for example, 2 links for which this is not true. For example, the effect of El Niño on inner monsoon is not well represented by the model, and also the effect of the inner monsoon on geopotential height over the Mediterranean, this is also off. So these 2, let's say, misrepresented links may help explaining why we see these differences in the previous plots. And again, we check for the effect of historical trends, strong inner monsoon and strong La Niña. And we see that there are like some links that are affected by these two events. And yeah, so to conclude, the idea of the paper here is to show a link between in this case, weaker inner monsoon and enhanced probability of having heat waves. So we first check the effect of inner monsoon activity on Etesians and temperature over the Middle East in first the short-term time scale, and then in like longer time scales, and we see that this influence goes via of the inner monsoon goes via the Etesians. Specifically, weaker Etesians are linked to a more probability of having extreme temperature over the Mediterranean. And there's, for the short time scale, good agreement between model and observations. And at interannual time scales, there is like some agreement between model and observation for Northern Africa, but not so much for the like northeastern part of the Mediterranean. And this is likely, or like it can be at least partially explained by these missed causal links between El Niño, the inner monsoon, and the circulation over the Mediterranean. So this is the last slide. This is actually our lovely institute in Potsdam during winter. And yeah, thank you for the attention, and I'm happy to answer any question.
Thank you. Perfect timing. So thank you for such an insightful talk. I think now is open for question. If you may either type your question or unmute yourself to ask directly. Yeah, just feel free to unmute yourself if you have any questions or comments.
I know that it's a lot of information in just like 40 minutes.
Yeah, sure. So while the audience is gathering, therefore, I would like to have a comment and a question. So your thoughts suggest that identify the causal link between the regional pattern and the large-scale phenomenon can support kind of more accurate modeling, or maybe increase the prediction skills for the extreme weather event. So I think this can help our policymaker to decide some climate policy or something, try to stop some, try to improve the human health. Given that the relationships of the extreme weather sometimes can be nonlinear, I'm just wondering, when dealing with the nonlinear dynamic, how my causal inference can improve this identification process because I noticed you mentioned by calculating the causal effects, you use the partials, linear correlation. So I just wondering how to deal with nonlinear dynamics, or maybe for instance, by combining the machine learning or something. Yeah, so I just wondering.
Yeah, no, that's actually a great question and comment. So yes, part of the idea behind this work is to kind of, on one side, checking or like looking at these like mechanisms that or like drivers that can lead to certain events. And of course, if we can identify weak points in a model, so like parts of these mechanisms that are not well reproduced. I mean, I have analyzed already like a couple of different systems in seasonal forecast or in the other paper in an Earth system model. And in general, there will be some links that are well reproduced, maybe with a little bit of bias. And then there's maybe like a few links that are really badly represented. And so this gives us an information on, okay, so what we need to be careful about, or maybe which weak points a certain model has in this like describing or reproducing certain mechanisms. So in this sense, yes, I don't do modeling myself, but ideally this can be useful information for the people that develop these models in case they have time to, or like they want to improve specific parts of it. And the question about linearity, yeah, that's a very strong assumption, of course. And while it kind of works fairly well in like first approximation, we of course need to keep in mind that we are only looking at linear interactions. And so the PCMCI algorithm by itself is also built to look at nonlinear relationships. The problem with that is that we need like more like longer time series to actually be able to exploit the nonlinear features of PCMCI, because the significance testing is very strict. So with nonlinearity, we need like more data, and for observations is maybe not enough. I would say it's at this time scale, it's enough for or for like the intraseasonal variability at 3-7 days. The 40-50 years of reanalysis are fine. But for example, for monthly, I didn't go too much into details, but it's actually not really enough to just look at the output with the same strict evaluation of the significance. So this is why I haven't tried to do much with nonlinear links yet. But yeah, especially for extremes, it is kind of important also to check whether the precursors that are identified behave more or less linearly. So in this case, I was looking at correlation maps, which of course can assume like linearity, but you can also look for precursors in composites that are like tailored to the extreme, and these don't need, like, they are not necessarily linear. So you could have that like a high in a certain region appears when you have a heat wave, but then if you look at cold anomalies, you don't see the corresponding like low in the same area. And actually, this is something that I still need to further investigate, but it looks like while these relationship at like short time scale are quite linear, also if I think about the composites that I've been showing, they look like the specular image of each other. But the effect of the Indian monsoon at interannual time scale doesn't look like it's linear. So basically, these like warming effect over certain areas that we see during a weak Indian monsoon years doesn't correspond to a cooling effect during years with a strong Indian monsoon. So it looks like in that case, the relationship is not really linear, which is also what is shown by the fact that the certain elements in the network change value when the background state changes. So there's not just a difference in the values of the time series, but there's really different in the network itself.
Cool. Yeah, it's always an issue to investigate the nonlinear, especially our time series is limited and our variable or dimension is quite high.
Yeah.
Thank you. Yeah, we still have time, so maybe 1 or 2 questions if you have. Okay, lovely. Yeah, I think it's almost 1 o'clock. So if they have no more question, I think, yeah, we appreciate you for sharing your time and expertise with us today. And I would like to conclude our seminar and thank you all of you for attending. If you have no more question, thank you.
Thanks again.
Thank you.
Bye-bye. Thank you, everyone. Yeah, Giorgia, so I will meet you later and thank you.
Yes.
We will discuss further in detail about research. See you.
Thank you so much. Have a nice afternoon.
Bye-bye.